Hi, good morning. Today we are going to start our next section, section 3.6, the double dual. Okay, now let V be a vector space over the field F and a V star be its dual space. V star is the set of all linear functional on V. Okay, let alpha be a vector in V. Then this alpha induces a linear mapping L alpha in V star defined by L alpha of f is equal to f of alpha for every f belongs to V star. Then L is a linear functional. Again, here we have given V is a vector space and V star is the dual space. That means V star is the set of all collection of all linear functional on V. Now we are defining a new mapping L alpha. What is L alpha? Let alpha be any vector in V, then alpha induces a linear mapping L alpha in V star defined by L alpha of f is equal to f of alpha. So L alpha is actually a mapping from V star to f, and it is defined by L alpha of f is equal to f of alpha for every f belongs to V star. Then the result says that L alpha is a linear function. Now we are moving to the proof. Let f comma g belongs to V star and c belongs to f. Now what is L alpha of Cf plus g? By definition this is equal to Cf plus g of alpha, and which is equal to Cf of alpha plus g of alpha, and which is equal to c into f of alpha plus g of alpha, and which is equal to c into L alpha of f plus L alpha of g, and this is equal to, therefore L alpha of Cf plus g equal to c into L alpha f plus L alpha of g. This implies our L is a linear, L alpha is a linear functional on V star. Suppose f is a linear functional on V star, then we call f belongs to, f is a linear functional on V, then we call f belongs to V star. So if L alpha is a linear functional on V star means L alpha belongs to V star star. That is L alpha belongs to V star star. Okay, that is V double star is the set of all linear functional on V star. Now the space of all linear functional L alpha on V star is called the double dual of V, and it is denoted by V star. The space of all linear functional L alpha on V star is called the double dual of V, and it is denoted by V double star. Now V double star is equal to set of all L alpha such that alpha belongs to V. Okay, that is actually V double star is the set of all linear functional on V star. Okay. Now we are moving to the definition. Remark: dimension of V double star is equal to dimension of V star, dimension of L of V star F, set of all linear functional on V star. So dimension of L of V star F, and which is equal to dimension of V star into dimension of f, which is equal to dimension of V star, which is equal to dimension of V. Therefore dimension of V double star is equal to dimension of V. Our next remark: if V is a finite dimensional vector space and alpha not equal to 0, then L alpha not equal to 0. That is, we have to prove L alpha not equal to 0 means L alpha is a non-zero linear function. Okay, so to prove L alpha is not equal to 0, what we have to prove? To prove f not equal, suppose f is some function, to prove f not equal to 0, what we have to prove? we have to prove there exists a alpha belongs to, suppose f is a function from a to b. To prove f not equal to 0, we have to prove there exists a alpha belongs to a such that f of alpha not equal to 0. Similarly, here L alpha is a function from V star to F. To prove L alpha not equal to 0, what we have to prove? We have to prove there exists a linear functional F such that L alpha of F not equal to 0. This is what we have to prove. Okay, we are choosing alpha not equal to 0. Therefore, we have to prove L alpha. In order to prove this, it is enough to show that there exists a functional f belongs to v star such that L alpha of f equal to f of alpha, which is not equal to 0. Now, given what is the given condition? Given condition is alpha not equal to 0. Therefore, if you take singleton set alpha, then it is linearly independent because alpha is not equal to 0. Therefore, this set is linearly independent. Now we can extend this alpha to a basis of v, say alpha 1, alpha 2, etc., alpha n. But alpha, if you put alpha equal to alpha 1, so this is a linearly independent set. So we can extend this as a basis of v, and this set, the extension is actually alpha, alpha 2, etc., alpha n, and we are denoting alpha 1 as alpha. Therefore, this set is a basis for V. Now, corresponding to this basis, there exists a dual basis f1, f2, etc., fn, and which satisfies fi of alpha j equal to delta ij. Fi of alpha j equal to 1 if I not equal to j, 0 if I equal to j. Now, if you consider f1 of alpha 1, then clearly by definition of dual basis, this is equal to 1. F1 of alpha equal to 1, which is not equal to 0. Therefore, because we are replacing alpha, we are taking alpha 1 is equal to alpha. Therefore, f1 of alpha equal to 1, which is not equal to 0. Therefore, there exists a f1 belongs to v star such that L alpha of f1 equal to f1 of alpha, which is equal to 1 and which is not equal to 0. Okay, therefore L alpha is not identically equal to 0. Clear? We have here we get a linear functional f1 and that is a in dual basis of v, such that this for this f1 of alpha is not equal to 0. Therefore this L alpha is not identically 0. Okay, hope it is clear. You must remember, if alpha not equal to 0, then L alpha is not equal to 0. Okay. Therefore, if alpha equal to 0, then L alpha, what about L alpha? That we don't know actually. But if alpha not equal to 0, then L alpha must be not equal to 0. Therefore, if you take L alpha is not equal to L alpha equal to 0, then clearly that implies alpha must be equal to 0. Okay, if we have L alpha equal to 0, then alpha must be equal to 0, because if alpha not equal to 0, then L alpha must be not equal to 0. Okay, note this. Now moving to theorem. Let V be a finite dimensional vector space over the field F. Okay, for each alpha vector alpha in V, define L alpha of F is equal to F of alpha F in V star. We are defining this map, and the map here defining a map alpha to L alpha is an isomorphism from V on to V double star. I'm repeating, L alpha for each alpha in V, we are defining L alpha is F is equal to F of alpha, F in V star, as we have defined here. Okay, we already defined L alpha of F is equal to F of alpha for every alpha belongs to, for each alpha belongs to F, and this map L alpha is a linear functional. That means L alpha belongs to V double star, that we already proved. Now here we are defining a map from, suppose some map phi from V to V double star as alpha goes to L alpha. Alpha goes to L alpha. So we have to prove this mapping is an isomorphism. So what we have to prove? We have to prove this map is a linear map. Also it is 1 1 and also it is 1 2. So define a map phi from V to V double star by phi alpha equal to L alpha, and we have to prove phi is an isomorphism. So first we are going to prove phi is linear. So you take some elements alpha comma beta belongs to V and C belongs to F. Now what is phi alpha of C alpha plus beta? And this is equal to L C alpha plus beta. Now what we have to prove? To prove this is linear, what we have to prove? We have to prove phi of C alpha plus beta equal to C into phi alpha plus phi beta. Okay. Now this is equal to what is phi alpha? Phi alpha is L alpha plus phi beta is L beta. We have to prove this. And this is L C alpha plus beta. We have to prove this. And both of these are functions. L alpha is a map from V star to F. Both are functions. So two functions f equal to g only if f of x equal to g of x for every x belongs to the domain. Therefore, here we have to prove L C alpha plus beta of f equal to C into L alpha plus L beta of f for every f belongs to V star. That is what we have to prove. Okay. So we have phi of C alpha plus beta equal to L C alpha plus beta. Now for every f belongs to V star, L C alpha plus beta of f is equal to, by definition this is equal to f of C alpha plus beta. But f is a linear functional. Therefore, this you can write as c into f of alpha plus f of beta. Now, but L of alpha, f of alpha is L alpha of f, c into L alpha of f plus L beta of f, and which is equal to c L alpha plus L beta of f. Therefore, if you take any linear functional f, L C alpha plus beta of f equal to c L alpha plus L beta of f. Okay, thus we get L C alpha plus beta of f equal to C L alpha plus L beta of f for every f belongs to V star. Okay, therefore this condition holds. Okay, that means L C alpha plus beta equal to C into L alpha plus L beta. That is phi of C alpha plus beta equal to C into L alpha is phi of alpha plus L beta is phi of beta. This implies phi is linear. Now we have to prove phi is 1 to 1. To prove phi is 1 to 1, it is enough to prove that phi is non-singular. Now what is phi is non-singular? Phi is non-singular means phi of alpha equal to 0 implies alpha equal to 0. This is the definition of a non-singular property. That is, phi is non-singular implies phi of alpha equal to 0 implies alpha equal to 0. So we are proving let alpha belongs to V be such that phi alpha equal to 0. This implies L alpha equal to 0. This implies alpha equal to 0. Because we have this result. We have already discussed this result. Here we have if alpha not equal to 0, then L alpha is not equal to 0. Okay, therefore if we consider phi alpha equal to 0, then we get L alpha equal to 0, which clearly implies alpha equal to 0. Because if alpha not equal to 0, then L alpha must be not equal to 0. Therefore, phi alpha equal to 0 implies alpha equal to 0. This implies phi is non-singular. Now we have to prove on to. Here phi is a one-to-one map and the dimension of V equal to dimension of V star. Therefore, clearly phi is on to. How this happens? We have a dimension of V equal to dimension of V double star. Okay, that is the range set. What is dimension of range? If you consider this, phi is a map from V2 V double star. Okay, therefore phi of what is phi of V? Phi of V is completely contained in V double star. Okay, and what about dimension of range of phi? Range of f. This space, this is contained, and dimension is dimension of range of phi. As phi is 1 to 1, nullity of phi is 0. So rank of phi is nullity phi plus rank phi equal to dimension v, and which is equal to dimension of v double star. Nullity is equal to 0. Rank phi equal to dimension of v double star. That is, dimension of range space is equal to dimension of v double star. Here, if range space is properly contained in v double star, then dimension of range is, if it is a proper subset, then rank of phi is strictly less than dimension of v double star using one result. Okay, but here we get rank of phi equal to dimension of v double star. That implies range of phi is equal to dimension of, sorry, range of phi is equal to v double star. Okay, that implies phi is onto. This is enough actually. There is no need to write all these things. We have phi is 1 to 1 and dimension of v equal to dimension of v double star. Therefore, phi is onto. This implies phi is an isomorphism. Therefore, v is isomorphic to v double star. Now moving to a corollary. Let V be a finite dimensional vector space over the field F. If L is a linear functional on the dual space V star, then there is a unique vector alpha in V such that L of F is equal to F of alpha for every F in V star. Okay. So it is easy. We have already from theorem 13, we get a map phi from V to V double star defined by phi alpha equal to L alpha is an isomorphism. That is, phi is 1, 1 and onto. That is, if you take any linear functional here, L alpha here, then correspondingly there exists a alpha belongs to V such that phi alpha equal to L alpha. Okay, but here L is any linear function on the dual space. Therefore, L belongs to our V double star. As phi is onto, there exists a alpha belongs to V such that phi alpha equal to L, and that that alpha is unique as phi is 1 to 1. So what we get, there exists a unique alpha belongs to V such that phi alpha equal to L. But by definition, phi alpha equal to L alpha. Therefore, we get L alpha equal to L. Okay. We have phi alpha equal to L alpha, and here we get phi alpha equal to L. Therefore, L alpha equal to L. Therefore, if you take any linear functional f on V star, L of f is same as L alpha of f, and which is equal to L f of alpha. Okay, this is the definition of L alpha. So there exists a unique alpha belongs to V such that L of f equal to f of alpha for every f belongs to V star. Clear? Now moving to our last corollary. Let V be a finite dimensional vector space over the field F. Each basis for V star is the dual of some basis for V. Last class we have proved if there exists a some alpha 1, alpha 2, etc. alpha n is a basis, then there exists a dual basis f1, f2, etc. fn. And this is a dual basis of alpha 1, alpha 2, etc. alpha n. Now here it is saying that for each basis for V star, for each F1, F2, etc. Fn, there exists a some basis for V, there exists alpha 1, alpha 2, etc. alpha n, and F1, F2, etc. Fn is a dual basis of alpha 1, alpha 2, etc. alpha n. Okay, now we look at the theorem. Proof. Let B star equal to F1, F2, etc. Fn be a basis for V star. And we have to prove there exists alpha 1, alpha 2, etc. alpha n, for which this is a dual basis. Now by theorem 15, here we are considering V double star. Okay, this is V star and considering V double star. So for this F1, F2, etc. Fn, there exists a dual basis L1, L2, etc. Ln for V double star such that Li of Fj equal to delta Ij. Earlier we are considering alpha 1, alpha 2, etc. Alpha n is a basis for V. Then correspondingly there exists F1, F2, etc. Fn is a dual basis. Here we are considering F1, F2, etc. Fn and considering in V star and considering its dual basis L1, L2, etc. Ln in V double star. Okay. So this Li of Fj satisfies delta Ij. So for each of these Li using this corollary, again this corollary, for each linear functional L, there is a unique vector alpha in V satisfying this condition. So for this L1, there is a vector for each I, there is a vector alpha I in V satisfy Li of F is equal to F of alpha I. Okay, and this is true for every F belongs to V star. Okay, now note that this Li is same as the earlier L is equal to L alpha. Here Li is same as L alpha I. So for each I, we get a alpha I here. Now consider alpha 1, alpha 2, etc. alpha I. Now we are proving this is a basis for V. For proving this is a basis for V, it is enough to prove that this is a this set is linearly independent because number of elements is already n and dimension of here we already proved dimension of V equal to dimension of V star equal to dimension of V double star. Dimension of V star is n, therefore dimension of V is n. Therefore, this set is to prove this is set is a basis. It is enough to prove that this set is linearly independent. For this, suppose C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n is equal to 0. Now apply f of C1 alpha 1 plus C2 alpha 2 plus etc. plus Fn Cn alpha n is equal to f of 0 which is equal to 0. And apply linearity property C1 f of alpha 1 plus C2 f of alpha 2 plus etc. plus Cn f of alpha n equals 0. What is f of alpha n? Here f of alpha I is Li of f. Therefore, using this result, this is C1 L1 of f plus C2 L2 of f plus etc. plus Cn Ln of f equal to 0. And this is actually C1 L1 plus C2 L2 plus etc. plus Cn Ln of f equal to 0 and which is same as this is actually same as 0 of f for every f belongs to V star. Some f g of alpha equal to 0 for every g belongs to. That means this g must be equal to 0. Okay. Therefore, from here we get C1 L1 plus C2 L2 plus etc. plus Cn Ln equal to 0. Therefore, but L1 L2 etc. Ln are linearly independent. Therefore, this implies C1 equal to 0, C2 equal to 0 etc. Cn equal to 0. This implies that alpha 1, alpha 2 etc. alpha n are linearly independent. Okay, therefore this form a basis for V. Now we have to prove whether Fi's are dual basis of this alpha 1, alpha 2, etc. alpha n. We have Li of f is equal to f of alpha I. Therefore, Li of fj equal to fj of alpha I. Now Li of fj, what is Li of fj? Li of Fj equal to delta Ij. Okay, delta Ij. Therefore, Fj of alpha is equal to delta Ij. This implies Fi of alpha j is also equal to delta Ij. Therefore, F1, F2, etc. Fn is a dual basis of alpha 1, alpha 2, etc. Alpha n. This implies given any f1, f2, etc. fn, there exists a basis alpha 1, alpha 2, etc. alpha n in V such that f1, f2, etc. fn is a dual basis of alpha 1, alpha 2, etc. alpha n. Okay, that's all for today's class. In the next section, we will discuss some problems related to this session. Okay.